So the title of my talk is facial structure of EDM cone and the intersection of a linear subspace. So this is a joint work with Dr. Mira Cesaro. So the talk is divided to two parts. The first part is about some theorems about the facial structure of the EDM cone. The second part is about the generic radius circle packing problem. So we will show you a proof of the weak version of this this problem. So this problem is raised by Louis Siran, Stephen Gottler, and Robert Connelly. Okay, so let's first see some start from the EDM cone. So let G be this orthogonal projection. J is I minus n over 1 over n e times E transpose. So this is the orthogonal projection on the orthogonal complement of the vector space of vector ones. So we consider this ENR, so this, to be the set of the EDM matrices with embedding dimensions not greater than R. So that is Y is in this set if only if Y is satisfy these conditions. So where SH is a hollow subspaces. So the EDM of all possible embedding dimension denoted as En from the cone. So it's IE En the set of all possible embedding dimension is a cone in the symmetric space n times n. Okay. So there's another name for this set. We call this ENR, R stratum of the EDM cone. Right. So it's made up of a matrices EDMs of embedding dimension not greater than R. Okay. So let's look at the face. Well, because we want to study the facial structures of the EDM cone. The definition of phase is the following, right? Basically, if you have 2 points, x, y is in the cone, and if the middle point of the 2 points is in this phase, then these any point are also in this phase. If we satisfy this condition, then it is a phase, and the phase is exposed if there exists a phi in Fc, such that F is equal to K intersecting the orthogonal complement of phi. So a phase is exposed if it's a cone intersecting a linear hyperplane. So if every face of K is exposed face, then it's facially exposed cone. So there is this theorem which says that every PSD cone, both the PSD cone and the EDM cones are facially exposed. So every face in these 2 cones are intersecting of hyperplane with the cone. Okay. So there's there are some theorems characterized as a face of the EDM cone, right? this theorem from these two theorems from Abdul Al-Fakir's book. So the first theorem says a phase of D1. So as D1 be a EDM matrix, then the phase of D1. So which means the phase that contains D1 as the point in the relative interior of the phase. So so for each EDM matrix, there's a unique minimal phase that contains this D1 and this D1 is in the relative interior. So that's the phase of D1 En. So this this is D1. This is the definition of D1. So the V is so we have V times V transpose is equal to J. So and then we have non-space of 1/2 V transpose D1. V is a subset of the non-space of V1 transpose dV. And another theorem is using the Gale space. So we said the phase of D1 is this D subset. The Gale space of D1 is a subset of Gale D. Okay. So we can actually characterize this phase of the EDM cone using the phase of the PSD cone. So we define this Linden's mapping that maps Linden stress mapping operator that maps the Gram matrix to an EDM matrix. And the inverse is K dagger is this one. So this is the inverse map. The inverse map maps EDM to Gram. So this there's another theorem says that if D bar is in the face of D1 of the EDM cone, then this D1 is equal to K of V1 S plus R V1 transpose for some S plus R. So this V1 S plus R V1 transpose is a face of the PSD cone. So it maps a face of PSD cone to a face of EDM cone. And we can also actually explicitly construct the hyperplane that exposes this phase. So in fact, phase D1 En is all such D, such that D the inner product D comma U1 transpose is 0. So this is a hyperplane in the symmetric cone, in the symmetric cone of in the set of a symmetric matrix. And this U1 is just the non-space of V1 transpose V transpose. So where this V1 is the following, right? V1 is this. So V1 is basically the range of V1 is the range of the it's just the coordinate of the point. The range of V1 it's just it's equal to the range of the coordinates matrix of the points in so we actually have this so similar to the PSD cone where we have this SNR S plus NR which consists of other PSD matrix of rank less or equal to R. So this is SNR is a union phases of the PSD cone. So similarly for EDM cone, we say that this R stratum or EDM with invariant dimension less than or equal to R is a union. Sorry, there's a union. There's a union sign of so there's a union of let's draw this here. union all the possible v. So this k of vs plus v, it transposes the phase of EDM cone, right? So this says that this R stratum is a union of all the phases of the PSD cone with embedding dimension less or equal to R. So this is gives a characterization of the R stratum. So here I have a conjecture. The conjecture is the following. So given a linear subspace, if L passes through the relative interior of the EDM cone, and also passes through the interior of the this R stratum, then L if L then L intersects this R stratum properly. So by intersecting properly, I mean the dimension of the intersection of the R stratum with L is the dimension of the R stratum minus the codimension of L, right? So you can let's say in a three in the three space. So if I have a plane, right, and if I have a line L, and this is plane, so the dimension of P is 2, the dimension of L is 1. So so the codimension of L is 2. So if they intersect properly, that means the dimension of P intersecting L is 2 minus 2 is 0, right? Well, that means that they are intersecting like this. This is if L happens to lie on this plane, then they do not intersect properly. So generically, like the two linear subspaces should intersect properly. Okay, right. So for this why am this I think this is true, this can be true. It is because if this dimension if the dimension of R stratum with L have lower dimension, this if there's only two possibilities, if it has lower dimension, if part A is L doesn't intersect the interior of the R stratum, and R if intersect the interior of the stratum, but it's tangent to this R stratum. Okay, so this is the only two possibilities that the L does not intersect the R stratum properly. So well, since we have a rule out that we rule that with the possibility of A, because L actually intersects the interior of epsilon R. So the only possibility is B. But if L intersects the interior of but if L is tangent to the stratum, the R stratum, and this R stratum happens to be the boundary of the R+1 stratum, right? So then I suspect that if L is tangent to epsilon R, then it should be tangent to epsilon R+1. So this is the conjecture. So I'm not sure. I don't have rigorous proof. So if anyone thinks this is wrong, just tell me. Please tell me now, and I'll be very, very, very grateful. If you think it's correct. So maybe I should leave for some questions for now. So are there any questions so far? Okay, if there's no question, then I'll continue to this second part. Okay, so well, I for this for this conjecture, although I don't know if this is true for any L, but I do have a theorem that if L happens to be the so-called the circle context space, so we will talk about definition later. So if L is the circle context space, and then this conjecture is true, and then we will prove it using the vertex splitting technique for the minimal rigid graph. Okay. So now let's look at the definition of packing space and the projection. So let's give a graph. The graph so give a graph G of VE with the edge length is more than it's bigger, it's no less than the number of vertices, and the graph is connected. So consider the linear system in V plus V choose two variables, xi and yij. So xi is the corresponding to the vertices, and the yij corresponding to the edges. Okay, so the linear system is given by these equations: xi plus xj equals yij, for ij being the edge set. So we do not denote this space, this solution space of this linear system as S. Okay, and then so there's an observation. So the solution of this linear system span V choose 2 minus E plus V dimensional space. That is saying that the codimensional S is E, right? Because there are a number of V choose 2 plus E variables. So X and X has I variables, and Yij has E variables, and the and the codimension is E because there are E constraints, right, of this xi xj plus equal to yj, and this yij is this matrix corresponding to the yij is the identity matrix. So the linear constraints are linear dependent. So therefore the dimension is this, and the codimension is E. So and then we consider the projection of this packing space S using this xy project to y by eliminating the si's. So the xi is is edge set corresponding to the edge. The yij that's not in the edge set are are basically arbitrary, right? So if y is in the is an edge, then there might be a linear relationship. If y is not in edge in the edge set, then yij is just arbitrary. So we call this circle context space. Why? Because we haven't we didn't add the inequalities xi plus xj less than yij. So the resulting so if we add this xi plus xj less r equal to yij, then we are actually imposing the circle packing constraint for the non-edges, right? So maybe I should briefly say something about the circle packing stuff. Let's clear. So I share my screen. So can you see my screen?
Yeah, we can see it. Okay.
So so suppose you have a so we have a graph, right? We have a graph, and so there are 1, 2, 3, 4. So what is the circle packing then? Basically, you have a circle that like this, and this. Well, this is not very accurate. Okay. So for each vertices, you have there's a radius. So R1, R2, so R3, R4, right? So this circle, this radius adds up to the it's the sum of the radius is equal to the pair of the edges. So R1 plus R2 is equal to E12, and R1 plus R3 plus equal to E13, etc. Right? R2 plus R4 is E24. So that's why I have a constraint like this in my circle packing space, right? I have a xi xj is equal to yij because I wanted this circle, this radius. So ri plus rj is equal to the length of the edges. Okay. So so this is so let's draw draw another graph that so let's say consider this graph. This is a k33 minus 1. So 1, 2, 3, 4. So this is a.
I think you mean k4 minus 1.
Yeah, k4 minus 1.
Yeah.
Thanks, Mira. So this is a minimal rigid graph. A planar minimal rigid graph. Well, there's a so you can definitely flip this triangle to the other side of the edge, but let's keep it this way. And so now let's have a circle packing. Well, so I have a circle like this. I have a circle like this, and I have a circle like this, right? And then I have another circle like this. So this circle, so now this graph has it's packed, but there's one edge, which is this edge, right? This edge, for this edge, E23, this actually is less than R3 plus R2, right? Because you can see the two circles, the two circles are actually overlap each other. So, but in reality, in the circle packing problem, you want this E23 is greater or equal to R3 plus R2, right? So, okay, that's why my S, we call it the circle context space. And if we add the inequalities, we call this circle, this is the real circle packing space. Okay, and let's now stop sharing. Okay, so so can you see my space? Can you see my can you see my screen now?
Yeah, we can see it.
Okay. So okay. So we have some observations, right, over this circle context space and the circle packing space. So the first is the dimension of the circle context space is at most 2v minus v plus v. So which is saying the codimension of S prime is at least e minus v. Because S prime has a how many S prime is the projection by eliminating the xi's, right? So there are only we choose two variables. We choose so the code dimension is at least e minus v, and we also observe that the dimension of the circle context space is equal to the dimension of the circle packing space. So dimension S prime is equal to the dimension of T prime. So we have this lemma or observation, which says if the graph is connected and the number of edges is greater or equal to the number of vertices, then the projection of the packing space actually has dimension 2 v2 minus e minus square parenthesis v minus ag. So I is the codimension of the circle context space S prime is e minus v plus ag, where ag is the column rank deficit of ax, where the linear system is a equals ax ay. So let's look at an example to make it clear. So consider a 4 cycle with the vertices being v1, v2, v3, and v4, and edges being this. So it's a cycle, right? So the linear system is given by this. So you can see here. This is my ax. Right? On the left, this is my ax, and on the right is the ey. So ax is the 4x4 coefficient matrix for x, x1, x2, x3, and 4. And ay is the coefficient matrix for these y's. So the solution to the system spans a 6-dimensional space because the number of vertices is 2 plus 4, and there are 4 linearly independent constraints. So 6 plus 4 minus 4 is 6. But however, the rank of ax So the rank, which is this matrix, this is the projection by eliminating the x edge, x, right? This rank is 3, and that's because of y14. So like this y14 is yeah, this one. This is y14 is equal to x1 plus x4. So it's actually equal to y12 plus minus y23 plus y34, right? You can see this. I have 4 cycle. If they are circle effect, like this, then this edge is y14 equal to this edge y12 minus this edge y23 plus this edge y34. So the rank of Ax is 3, and that means the rank the column rank deficient is 1, and the projection of has therefore has dimension 5 instead 4 instead of 6. So the codimension is 1. Okay. So now I have this is the main theorem. So we actually prove that all the planar minimum rigid graph, Lamang graph, have a rank deficient 0. Okay. And then from this theorem, min 0, we conclude that the dimension of the two stratum intersecting the circle context space, the intersection of these two set is the intersection is a property. So therefore, the dimension of intersecting of the two stratum with S prime is the dimension of the two stratum minus the codimension of S prime. So the theorem says of course this graph G has to be a minimum rigid planar graph. So it's a Lamang graph, and V is equal to the N is the number of vertices. So since this G is the Lamang graph, we have this E number of edges is equal to the number of vertices times 2 plus 3 minus 3. Hence, the codimension is just the dimension of the. So the dimension of the two stratum. It's from the rigid theory. It's just 2v minus 3 because the Lamang graph is a minimal rigid, right? And it has edge. So all these other edges are actually determined by the edges in the Lamang graph. So the dimension of the two stratum is 2v minus 3, and the codimension is E minus v from this because the rank deficient is 0. Okay. Therefore, it's equal to v. So let's look at the proof of this theorem. So let's first try to prove min 0. So the proof is using the induction idea. The induction hypothesis is the following. So we assume the base case is a triangle, and AX has no rank deficient. Right. So we start from a triangle, then the rank deficient is 0. Because there's no no 4 cycles, right? like for example, this in this triangle, there's no y1 2 y2 3 y1 3. There's no linear relation between these three edges, and right. So y1 2 is x1 plus x2, y1 3 is x1 plus x3, y1 2 3 is x2 plus x3. So there's no rough deficient. So the induction is we actually when we start from triangle, this triangle has no rank deficient, and then the corresponding AX has no rank deficient. So if they are actually in the reasoning of the hyper induction, if they are independent edges are marked, if they are independent edges, then it's marked as independent, as dependent. So the dependent edges are marked, and at each step, there is exactly one cycle of the unmarked edge, and it's odd. So basically, in this circle context space, if you have a circle of even length, right? If you have a circle of even length, so maybe 4, might be 5, might be 6, then you have a linear relation, right? So this edge is equal to this edge plus this one minus this one plus this one minus this one plus this one. So in each step we use a planar minimum rigid graph inductive construction by Fouquet, using only the plane vertex splits. So we start triangle. We at each step we increase the graph by using this plane vertex splitting. So we add one edge, one vertex, and two edge, and it's shown that all the planar minimum rigid graph can be constructed by this vertex splitting technique.
Faye, can I interrupt for a second?
Yeah.
So I think you want to say you have a planar minimally rigid graph. So when you say dependent edges, you mean dependent edges in the even cycle matroid. So I think you. Yeah. Okay.
Yeah. Thank you for the fact. Yeah. Yeah. And then so each so let's draw a graph. Let's use a picture to show the idea of the proof.
We can't see your picture.
Yeah, I'm just sharing my screen. So okay. So let's start from a triangle, right? So in each step, I suppose this is my U, this is V. So I split this V. So this becomes a V1 and V2, and then I add a version here, and then this V1 V2 is marked red. Why? Because the V1 V2 is on a even cycle, right? It's on this even cycle. So it's a dependent edge on the even cycle matroid. And then I can so I continue. So there are three cases. Cases 1, U, this so there after this marking this one as red. Then there is there's no even cycle edge, right? So you can see that there's only one cycle which is out, which is 3 cycle. So there are three cases. Is UV is if this is this odd cycle, C contains UV, and 2 if what's the proof? If the other cycle contains V, but not U, and 3, if C this even cycle C does not contain contain V. So contains UV, contains V but not U, or doesn't contain V. So in all these three cases, we can actually this V1, V2 can be marked as a dependent, and the odd cycle of C of the unmarked edges can be either returned or modified into another odd cycle. So there's no other new cycles of the unmarked edges are added. Since the induction hypothesis holds, right? So for example, I have a so I just showed this first case UV C contains both U and V, and then I can continue. Suppose this suppose I have a case 2. So all cycle C contains V but not U.
Faye, I think,
yeah.
Can I interrupt for a second? So you want to point out that the induction step is the splitting of a vertex V into V1 and V2, right?
Yeah.
So you had a vertex V which has been split into V1 and V2. Okay.
Yeah.
Right.
Thank you.
Yeah.
This all cycle contains V but not U. Let's see. This is after the first vertex splitting, and this contains V, but not U. And then I can split this case, this vertex. So V1, V2, and then I mark this as red. And again, I also this V you can this V1 V2 V1 V2 is in a even cycle is in a cycle of evenness. Right, because you can see it's this one. So therefore, V1 V2 is also dependent in the even cycle matroid. And the third case, if C doesn't contain V, well, let's C doesn't contain V, so C is the only odd cycle. Maybe this is my V. This is V. This is U. And then I create split this V1 V2, split V as V1 and V2, then I have a like this, and wait, yeah, like this. Right. Is this correct? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6.
Well, you want to have an edge from U to V2, right?
Yeah. Yeah. So the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. V is 6. Yeah. V is 6. So yeah, 2V minus E is 3. So again, this V1, V2 is also on the 4th cycle. So like this. So this one. We want it is on the 4th cycle. So this one, this. So 1, 2, 3, 4. Yeah. So there's a 4th cycle, I think. So it's again it's linearly dependent. So we mark this as red. Okay. So let's stop sharing. So in other 3 cases, I can always mark this V1, V2 as dependent, and there's no new cycles are introduced. So there's only one cycle of odd length. So therefore the rank deficit stays 0, and this is proved. So to prove the second theorem, which is this theorem, it said this intersection is proper. Well, we can just we can actually just use the proof of the main theorem. This previous theorem. So let's share screen. Yeah. So at each step, my vertex splitting. We actually so for example, in this graph, when I mark this, I mark V1, V2 as red. So this vertex actually, this vertex is actually independent in the V1, V2 is independent in the rigidity matrix, in the rigidity matrix of G, right? Because this graph here is a minimal rigid graph. So V1, V2 is independent. Well, that means I can change this the length of V1, V2 in the local neighborhood, and without changing the length of other edges. I can So this means V1, V2, V1, V2, adds one more dimension. One more dimension to this stratum, right? This stratum, two stratum. So the induction, so let and those this V1, V2 happen to be linearly dependent in the even cycle matroid. So V1, V2 is a dependent linear is dependent in the even cycle matroid, but independent in the rigid matroid. Therefore, I can say let G be obtained from G by vertex splitting, and so V prime so is equal to V plus 1. So there's a one more edge added, and one more vertex added, and two more edges are added. And then I have this dimension of plus 1, 2 intersecting S prime G is 2V is 2 V prime minus 3 minus 1 minus the E minus V. That's because well, I'm adding two edges, right? But one of the edges is becomes dependent in the rigid matroid. One more edge is one edge is dependent in the even cycle matroid, and the other one is independent in the rigid and it's independent in the rigidity matroid. So therefore, I have this this relation, and this happens to equal to 2 V prime minus 3 minus E prime minus V prime, and this is the relation we want to prove. And therefore the theorem is proved. Okay, so let's. So yeah, let's see the connection with the generic packing problem. So a planar graph is said to be triangulated, or also called a maximum planar, if the addition of any edge to the results, any edge, if the addition of any edge results in a non-planar graph. So we have this well-known KAT theorem. So for any planar graph, there is a circle packing representation after completing the planar graph into a triangulation. So the graph is called the tangency graph of the circle packing. So there's a question which asks the generic they call the generic radius circle packing question. So given a set of generic radii Ri, what has so this generic radii are just a coins, right? You can think about this. I have a bunch of coins. Like a bunch of coins. So which each coin, the radius of each coin is it's Ri. So this is the circle packing graph. this is the tendency graph. Something. Yeah. Given this, we are given this radius, right? Given this point. So what are the possible tendency graph? So you can see from this example, this graph happened to be k4 minus 1. So it's a Lemon graph. So then there's a question which asks if this is always true, right? If you have a generic radius of coins, then if you squeeze them, right? If you actually like so I have a bunch of coins, I just press them together until there's no possible movement. Then the contact tendency graph is the planar Lemon graph, and this theorem is the conjectured by Connelly, Kotler, and Siren, which says that any planar Lemon graph which after triangulation have this KT packing do have a generic radius two-dimensional packing and we have this here. It says if a packing has a generic radius, then the allowed motions are all rigid body motions, if and only if the packing has exactly 2n-3 contacts. So if we have less than 2n-3 contacts, then they are non-rigid body motion. So we can actually move it until it's rigid, and then so until we have rigid, then we have the maximum contacts, which is 2n-3, and this is happen to be a Lemon graph. So therefore, this conjecture implies that so for the for given a generic radius coins, then you can then suppose it has the maximum contacts, then the graph should be a planar Lemon graph. So why this is related to this dimension? Because to be generic, it means that we have v points, right? We have this is coins. So each a generic means this dimension, the dimension of the this dimension should be v, right? So this dimension should be v. So each radius can move. It's independent, and that's why that's what we call it's the genericity of the radius. So basically, we have proved that this conjecture, this generic radius packing conjecture, without the non-edge packing constraint. So that means if we allow this non-edge to overlap the circle of the non-edge to the circles on the non-edge set overlapped, then this is true. And in fact, this proof is valid for all the 2D minimal rigid graph that can be obtained using the vertex splitting and Hannibal-Wang extension, which includes the planar rigid Lemon graph, but maybe more. So if we have proved that this is true, if we can prove that this is the dimension of the intersecting with T prime is also V, then we will prove the conjecture of the previous conjecture. So why I think this is true, because remember T prime is just it's just S prime intersecting some linear inequalities, right? Some kind of linear inequalities. Well, and usually, and this when you add some linear inequalities, this doesn't actually affect the dimension. So so this so it's kind of reasonable to assume that the dimension of this tool is the same. So So yeah, so this is all of my talk. Thank you for listening. And so I have some references. So now it's time for questions.
Thanks.
So,
are there any questions?
So, Faye, you've proved the. Sorry, I was a bit lost on this. So you haven't proved the conjecture of Connolly, Gortler, and Thuran.
Yeah, we haven't. Yeah, we haven't proved that. We proved this. We put this without this non-edge packing constraint.
Ah, okay. So you've done it for like circle contact graphs or something like this.
Yeah, circle contact graph. The circles are allowed to overlap on the non-edges.
Ah, okay. That's quite cool. Okay.
Yeah, and if this is because of this dimension of 2, this S prime is equal to V. If we add the dimension, the circle packing constraint, then this this will be T prime is an S prime. And if this is true, then this proves the whole the conjecture.
So you proved it for the you proved dimension this thing with S prime is equal to V.
Yeah.
And you can prove. Yeah. Okay.
I want to prove that the other one, the T prime is also V.
Mm-hmm. Okay.
So the sort of positive thing is that if this includes now all kinds of minimally rigid graphs which are not necessarily planar. So in other words, we've proved this left-hand side intersection. So circle contact graph or whatever has a generic radius realization, even if that graph is potentially not planar, but it's just produced by vertex splitting and Henneberg-1 extensions. So in other words, in the proof, nowhere it is true that every planar minimally rigid graph can be obtained in this manner, but there are others that can be obtained in this manner.
Yeah. Is there any sort of chance that you can get it working for Henneberg 2? Or is
Henneberg 2, so we can show that it fails. The rank deficit theorem kind of fails for K33. And K33, as you know, needs a Henneberg 2.
Ah, okay. So it doesn't work for all of them, but it works for something in between Line graphs and planar line graphs.
Correct.
This category between the two where it works. Okay.
Correct. So we don't need to put, in a way, because these inequality, non-edge inequalities are gone, there isn't an explicit planarity condition in a way. It just sort of falls out of this interaction between the even cycle matroid and the rigidity matroid.
Yeah, there didn't seem to be anything to do with planarity in this. So
yeah,
because I mean, you didn't use topological vertex splitting, did you? You just did vertex splitting.
Yes, that's right.
Is it conjectured that this proof will be true? So the class of graphs where it's true is exactly those where you can get them from vertex splits and Henneberg-1 extensions.
No.
No. Okay.
Yeah. So I mean, we know it works for these. Maybe not. Maybe it works for others. We know there are some cases where it doesn't work, where this type of construction doesn't exist, but that doesn't mean much either.